When you point a strobe light at a fast-spinning wheel and match the flash exactly to the rotation rate, the wheel appears to freeze. If you slightly desynchronize the flashes, the spokes seem to crawl backward. Speed the wheel up enough, and the distinct spokes disappear into a continuous blur. The ODTOE framework categorizes this as a level 1 reality. What you perceive is strictly dictated by the sampling rate of the instrument you are using to look at it. The frozen wheel is a chart-dependent illusion. You are capturing a single, arbitrary slice of the object's behavior and mistaking that isolated measurement for its true state. Relying on a single sample rate creates a distinct vulnerability. The instrument filters out the continuous truth, leaving a blind spot when we try to navigate the physical world. Global positioning systems operate on a similar dependency. Modern navigation is essentially a chart constructed from external measurements. A GPS receiver constantly listens for synchronized pulses from satellites in orbit, calculating its location strictly through those incoming signals. Looking at early hardware like this Texas Instruments navigation unit, the bulk of the conical antenna highlights an absolute reliance on capturing an outside signal. Because the system requires that external handshake, the connection can be denied. Bad weather, targeted electronic jamming, or signal spoofing can sever the data feed. A targeted disruption to that external feed renders the receiver blind. True autonomy requires a system that tracks motion without referencing the sky at all. ODTOE defines an alternative, Level 2 and Level 3 realities. These are physical properties that survive any chart and ignore the observer entirely. We call these basis invariants. They are absolute structural facts that remain consistent, no matter what frequency you use to sample them. The measurable anchor of this invariant reality is the Sagnac effect. It is a physical response that cannot be faked or altered by outside observation. If you split a continuous wave and send the halves in opposite directions around an enclosed loop, the rotation of the device itself forces the waves to travel different distances. When they recombine, they are slightly out of phase. That phase offset guarantees rotation occurred. It extracts proof of movement directly from the local environment. For decades, physicists measured this specific phase shift by firing light photons through precision optical setups. By routing that light through kilometers of coiled glass, this photon-based method matured into the commercial fiber optic gyroscopes that guide commercial aviation today. The 2026 breakthrough replaces the beams of light entirely. Instead of routing photons, physicists are routing matter waves built from actual atoms. This chart shows the physics output. Left, the mass energy signal of a photon. Right, the mass energy signal of an atom. The Sagnac response scales directly with mass energy. Because atoms have massive weight, the right column explodes upward. The matter wave signal is 10 billion times larger. Substituting matter for light amplifies a microscopic physics anomaly into a robust mechanical signal. The hardware becomes sensitive enough to detect the exact rotation of the Earth. This brings us to quantum inertial measurement units. Engineering groups like QCTR and Inflection are taking these atom-interferometers out of the laboratory. The resulting hardware detects rotational changes roughly 1,000 times better than the top-tier fiber optic gyroscopes on the market. This extreme sensitivity pushes the system drift rate below 1 meter of error per hour of travel. Crossing that specific threshold means pure dead reckoning. Calculating your current position based only on a previously known position and measured speed is genuinely practical over very long durations. The system tracks location internally. Without an incoming signal to target, the feed is impossible to jam. Navigating by a GPS receiver is like studying the spinning wheel under the strobe light. You are trusting a level 1 illusion built on a fragile, interruptible chart. The atom gyroscope requires zero external input. It calculates its trajectory while moving completely sealed inside a pitch-black void. The engineering rule derived from the ODTOE framework is absolute. A robust system never navigates by a chart-dependent appearance. Next-generation quantum navigation operates underwater, operates deep underground, and through heavy electronic interference because it reads rotation directly off the physical basis of the universe. The future of position tracking discards the sky. It looks inward, relying on the undeniable mathematical invariance of reality itself.